Today we're going to talk about limits that involve infinity. There's two different ways that you can have a limit that involves infinity. One is that you're looking at, well, what happens as x becomes large without bound, either positively or negatively, either one. Then we'll also look at ones where at a particular value of x, the function becomes large without bound or negatively large without bound. Okay, so those will be the two different things that we're looking at. The first one is a horizontal asymptote. This is a definition that hopefully you did in pre-cal. I'm not sure if you did or not. It's not a big deal. But if you've got a horizontal asymptote, it has to follow this. The line y equals b is a horizontal asymptote of the graph of the function y equals f of x if either the limit as x goes to infinity of f of x is equal to b, or the limit as x goes to negative infinity of f of x is equal to b. Now, almost all of the functions that you're most familiar with, actually I would say all the functions that you're most familiar with, the limit as you go to the left and the limit as you go to the right are both the same if they're a number, if you had a horizontal asymptote, like with rational functions, right? There was the asymptote to the left and the asymptote to the right were the same. It's possible to have functions where they're not the same. And you haven't really had any experience with that. So let's take a look at this one. We want to identify all horizontal asymptotes of this function. F of x is equal to 3x over the square root of x squared plus 1. So what we're interested in finding is the limit as x goes to either positive infinity or negative infinity. We'll start with positive infinity of f of x. Now, we could then substitute in the function, limit as x goes to infinity of 3x over the square root of x squared plus 1. Now, one of the things that we will do a lot of, and hopefully you've done some of this in pre-cal at least, is that when you're looking at a limit as x becomes large without bound, we look at what are called the dominant terms. You may not have used that word, or those words, but in the numerator, there's only one term, right? So by default, it is the dominant term. In the denominator, as x gets really big, what matters way more than the other term? Does x squared matter more, or does the 1 matter more? The x squared matters a lot more, but it is the square root of x squared. And this is why this one is a little different. Because the square root of x squared, by definition, and I find that almost no students know this one, and I think it's just because there's no real, place that it has to get taught. But the square root of x squared is the absolute value of x. Ooh, might I actually get this? Missed him again. Man, this mosquito is driving me nuts. Now, as x goes to infinity, that'll be the limit as x goes to infinity of 3x over, if we're looking at the absolute value of x, and x is getting really big, it's just x, right? Yeah? And then x divided by x is 1, so this is 3. So one of our horizontal asymptotes is y equals 3. All right, Now, let's look at what happens when we go the other way. If we do the limit as x goes to infinity of f of x, and let's not spend all our time writing all the steps out. We need to get to this step where it's 3x over the absolute value of x. So the limit as x goes to negative infinity, I didn't write the negative here, sorry, negative infinity of 3x over the absolute value of x. Now, if missed him again. If x is a negative number, what do you have to do to take its absolute value? So if I have negative 6, how do I take its absolute value?
It's just 6.
Wait, I'm sorry, you both spoke at exactly the same time. Do what?
Get rid of the negative?
Get rid of the negative. How, mathematically, do you get rid of the negative? It does not involve an eraser.
Multiply by negative 1.
Multiply it by negative 1. So this is going to be the limit as x goes to negative infinity of 3x over the opposite of x. Now when you divide x by x and get 1, we get that this is negative 3. This function has two different horizontal asymptotes. So the horizontal asymptotes are y equals 3 and y equals negative 3. Interestingly enough, just a quick side note, this problem, or one very similar to it, showed up on the AP exam, about 10 years ago, and they had to throw it out because it was totally non-predictive of whether a student got a 1, 2, 3, 4, or 5. People who got a 5 missed it all over the place, as did people who got a 1. Very few people knew how to do it. All right, so remember that if you've got a limit, if you've got 0 over something non-zero, well, that's 0. If you've got something non-zero over something that's getting close to 0, then that's either going to go to positive infinity or negative infinity, depending on the sign of the numerator and the sign of the denominator. And you're like, wait a minute, 0 doesn't have a sign. Well, if we're approaching 0 from the left, it has a negative sign. And if we're approaching 0 from the right, it has a positive sign. If you get something infinite over a non-zero number, well, that's infinity. If you divide infinity by any number, no matter how large, you're still going to get something infinite. And if you have a non-zero divided by infinity, that's going to be 0. If the denominator becomes infinitely large, you've got a very small fraction, no matter how big the numerator is. That makes sense? So, let's take a look at this one. The limit as x goes to infinity of sine of x over x. Well, as x goes to infinity, sine just keeps oscillating, right? Does it have a limit? No, it just keeps oscillating back and forth. But the denominator is going to an infinitely large value. So if I have something that's in between negative 1 and positive 1 all the time, as sine is, and I divide any of those numbers by something that is infinitely large, what am I going to get? 0. Now, for a problem like this one, where we're trying to find the limit as x goes to infinity of 4x plus sine of 5x over x, what we need to do is use a little bit of algebraic manipulation to rewrite it as two separate fractions. 4x over x plus sine of 5x over x. We can do that because both of those parts of the numerator are over x. Then we can rewrite that as the limit as x goes to infinity of, well, 4x over 4 is just 4, right? Plus, and here's where it gets a little bit tricky. Remember that yesterday we showed that the limit as x goes to 0 of, and I don't remember which one we did. We either did x over sine of x or sine of x over x was 1. That's one that you really should just memorize. The trick to it, though, is that it has to be sine of something over the same something. Right? It was sine of x over x. So the argument of sine, what you're taking the sine of, has to be exactly the same as the other part. And is it here? No. So we have to use a little bit of algebraic manipulation to make it be what we want. We're going to rewrite this as 5 times the sine of 5x over 5x. I have just multiplied by what a friend of mine used to call a fafum, a fancy form of 1. So that's going to be 4 plus the sine of 5x over 5x is going to go to 1 times 5 is 5. So this is 9. Bugger it all day. I totally did that wrong. Crap a bucket. I'm so sorry. Back up a couple of steps. I was doing it as x went to 0. Was x going to 0 here? No. X was going to infinity. As x goes to infinity, sine of 5x just oscillates really super fast. But the denominator is still going to something infinitely large. So what is that going to go to? 0. So this is just 4. Sorry about that. This is how you get in trouble when you anticipate something rather than actually reading what's there, and I'm really bad at it. I'll be like, oh, I'm sure I'm going to do one of these, and no. All right, in behavior models, the in-behavior of a function can frequently be modeled by the dominant term, as we were already talking about earlier, as x goes to plus or minus infinity. For polynomials, the dominant term as x goes to plus or minus infinity is the leading term, which makes sense. It has the highest exponent. So let's find in-behavior models for this. So as x goes to infinity, f of x can be approximated by 2x to the 5th over 3x squared, which is 2/3 x cubed. So y equals 2/3 x cubed is an end behavior model for this. That function can be well approximated by just using 2/3 x cubed. Let's take a look at this next one. as x goes to infinity, g of x can be approximated by, again, just taking the leading terms, 2x cubed over 5x cubed, which is 2/5. Y is 2/5 is our end behavior model, which is another way of saying the horizontal asymptote is 2/5. Right? The graph will become indistinguishable from y equals 2/5. Now, for this next one, we're going to have to, with these, since they were polynomials, we only needed to look, or rational functions, which is a polynomial over a polynomial, we only needed to look as x goes to infinity. For anything else, we may need to look at both x goes to infinity and x goes to negative infinity, and that is true here. So, as x goes to infinity, h of x can be approximated by, well, let's think about that for just a second. I've got x, so I've got something that's getting really big, but I'm adding e to the negative x. Well, remember, e to the negative x is equal to what? As a fraction.
1 over.
Yeah, 1 over e to the x. So the denominator is getting really, really big. What is that fraction getting close to then? 0. So as x gets really big, this is getting really close to 0 plus the x. So on the right-hand side, my end behavior model is going to be y equals x. It's going to just start looking like, the identity function. But as I keep doing that, as x goes to negative infinity, now, if x is going to negative infinity, those negatives are going to cancel, right? And I'm going to have e to a really big power. Which is more important or more powerful as x goes to negative infinity then? X or e to the negative x? Yeah, e to the negative x. Exponential functions beat the crap out of polynomial functions when they get to the end. So h of x is approximately going to be equal to e to the negative x. That's the end behavior model on the left. So the right end behavior model is y equals x. The left end behavior model is y equals e to the negative x. And honestly, no one's ever going to ask you a question like this on the AP exam, but it is a good way to think about infinite limits as what is the behavior model. All right, let's take a look at infinite limits as x approaches a. The line x equals a is a vertical asymptote of the graph of the function y equals f of x if either the limit of as x approaches a from the left of f of x is either positive or negative infinity, or the limit as x approaches a from the right of f of x is positive or negative infinity. Either way is fine. So for rational functions, which you did a good bit of in Algebra 2, and did you do some of those in pre-cal again?
Yeah, a little bit.
A little bit? For rational functions, any value of x which makes the numerator a non-zero real number and the denominator 0 will indicate a vertical asymptote. right? When you had something that wasn't 0 over 0, you knew you had a vertical asymptote there. That sound familiar at least?
Yeah.
So, just real quick, if we were looking at f of x is equal to x plus 3 over x squared plus 4x minus let's make this 6x minus 8. Remember that what you had to do is go, okay, I'm going to factor that, and that was x minus, oh man, I've totally stuffed this problem up. This is why I don't make these up off the top of my head. X minus 4, x minus 2. So this has a vertical asymptote. At x is equal to 4 and at x is equal to 2. And the reason for that is as we approach 4 or 2, my function is either going to go up infinitely or down infinitely, right? Okay, let's go over questions from the homework then. We do have a little